If we really want to solve the mystery of what truly controls Earth's climate, we can't just be looking at the last few hundred years. We have to become deep time detectives. The crime scene isn't just a city block, it's the entire solar system. And the timeline? It spans 4.5 billion years. So let's grab our magnifying glasses because this investigation is about to get started.
So, where do we even begin this story? Do we start right here, around 1750, with the Industrial Revolution? Or do we need to go way back? All the way back to the very beginning, 4.5 billion years ago. Well, it turns out to find the real forces driving our planet's climate, we have to think much, much bigger.
Okay, so first things first, we've got to survey the scene of the crime. But this isn't about clues here on Earth, not yet anyway. This is all about establishing the vast, stable, cosmic platform that even allows Earth's climate to operate the way it does. And just so you know, this whole line of thinking, it's really grounded in the work from the book Earth Climate History. And its core argument is powerful. To truly understand our Earth, you first have to understand its place in the cosmos. It's not just about weather, it's about astrophysics. So our first piece of evidence for this stable neighborhood is this big guy right here, Jupiter. Its enormous gravity acts like a cosmic vacuum cleaner, or maybe you can think of it as a goalie for the inner solar system. It's constantly deflecting and capturing countless asteroids and comets that would otherwise be headed straight for us. Seriously, without Jupiter, Earth would just be a cosmic shooting gallery. And then there's the second key player, our moon, which, by the way, is unusually large for a planet our size. Its gravity is the reason we have predictable seasons. It acts like a stabilizer, preventing Earth's axis from wobbling all over the place. Without the moon, our planet's tilt could swing wildly, creating total climatic chaos, kind of like what we see on Mars. Our moon is our climate stabilizer.
All right, so our cosmic crime scene? It's secure. We have a bodyguard in Jupiter and a stabilizer in the moon. Now that we've established that stable platform, our investigation can finally turn to the physical evidence, the actual fingerprints left behind by climate itself, right here, on our own planet.
And that brings us to clue number 2. After sifting through billions of years of history, scientists stumbled upon something absolutely remarkable. It turns out there's a natural, repeating rhythm in Earth's climate, a kind of planetary heartbeat that's been pulsing for nearly 1 million years.
But where do you even look for evidence of a planet's heartbeat? It's not like you're going to find it in a rock you can pick up or in a dinosaur fossil. The most crucial clue of all is locked away in the most remote places on Earth, deep inside ancient ice.
So ice cores, they're pretty much exactly what they sound like. They're these long cylinders of ice drilled from the depths of places like Antarctica. Each layer of ice represents a year of snowfall, and this is the amazing part. Trapped inside that ice are tiny bubbles of Earth's ancient atmosphere, perfectly preserved. They are, quite literally, time machines. And here's the crazy part. When we analyze 800,000 years of this ice, this stunning pattern just pops out. You get a long, cold ice age that lasts for about 90,000 years, and then it's followed by a rapid warming into a brief warm period, kind of like the one we're in right now. And then the whole cycle just repeats. This is Earth's natural rhythm. So let's really dig into the data from those little atmospheric bubbles. During the coldest parts of an ice age, global temperatures were about 5 to 10 degrees Celsius cooler, and CO2 levels hovered around 180 parts per million. Then, during the warm periods, CO2 would jump up to about 280 parts per million. The key thing to see here is just how tightly temperature and CO2 move together. They're like dance partners. So look, the crucial takeaway here is this. For at least 800,000 years, the evidence shows that Earth's atmosphere had a natural ceiling and a natural floor for CO2. It just bounced predictably between a low of about 180 and a high of about 300 parts per million. This was the planet's natural comfort zone.
So, where are we today? We're here, around 420 parts per million. Yeah, we're way, way outside that natural operating range that held for nearly 1 million years. The ice core data makes that crystal clear.
Okay, so we found this incredibly clear rhythm, right? This 100,000-year beat. But what's actually driving it? What's the pacemaker for this massive planetary cycle of ice and warmth? Well, that leads us to our third and final clue. And the answer isn't something on Earth. It's not volcanoes, it's not changes in the sun's output. The force that's setting the timing for our ice ages is something way bigger. It's a gravitational pacemaker.
You see, the fingerprints, they don't belong to any suspect here on Earth.
They come from the constant, gentle, gravitational tugs of our planetary neighbors. The grand architecture of the solar system itself is what's pulling the strings.
What happens is these gravitational tugs create these tiny, but totally predictable changes in Earth's orbit. We call them Milankovitch cycles. Basically, three things change over long periods. The shape of our orbit goes from more circular to more oval-like, the tilt of our axis rocks back and forth a bit, and our whole planet wobbles on its axis, kind of like a spinning top that's starting to slow down. These little changes add up to alter how much summer sunlight hits the northern hemisphere, and that is the trigger for starting or ending an ice age.
So who are the culprits doing all this pulling? Well, Jupiter and Saturn are the main architects. Their gravity is what shapes most of our orbital path. But get this, a pretty recent discovery shows that even Mars plays a key part in setting that 100,000-year ice age beat. And the steady gravitational dance between Venus and Jupiter creates this incredibly stable 405,000-year cycle that acts like a cosmic metronome, keeping the whole solar system perfectly in rhythm.
All right, we've gathered all our clues. We've looked at the cosmic crime scene, we've analyzed the planet's own records, and we've dusted for the gravitational fingerprints of our neighbors. It's time to put it all together and finally close this case.
So, what's the verdict?
Clue number 1. Earth sits on this remarkably stable platform, protected by Jupiter and stabilized by the Moon. Clue number 2. The planet has a natural heartbeat, a predictable 100,000-year rhythm of ice and warmth, proven by 800,000 years of evidence from those ice cores. And clue number 3. This whole rhythm is driven by a gravitational pacemaker, the subtle, predictable orbital wobbles caused by our planetary neighbors.
So really, the big takeaway is this. Earth's natural climate system is a massive, interconnected machine. It changes in predictable ways, and it's all driven by the slow, magnificent gravitational dance of our solar system, operating over timescales that are just immense.
You know, when you really step back and look at the whole 4.5 billion-year story, you realize Earth's climate is like this incredible symphony, with movements that take 100,000 years just to play out. And that really leaves us with one final big question to think about. Are we now writing a brand new and much faster movement to that ancient symphony?